side, it has to be highly reflective. So when the laser shines towards it, it will go through without having much reflection. And so to get that combination is actually very, very difficult. So this is very new research. And we're trying to pass a laser within the range of 700 to 900 nanometer, and with a mid-band of somewhere around 785.5. This is a low end. This is mid-band. And so we've come up with a number of different possible combinations to be able to achieve this. Again, high index, low index, reflective layer, and achieving as much as 99.49% transmission. So, I mean, you might ask, what does this look like? This is another highlight where there is integrated optics, which essentially from the laser gain medium, which I showed you earlier, I mean, as the light's going through it, you go to 780 nanometer, you come all the way back to a highly reflective mirror, which would normally be out here. So the whole idea is you take that and combine it, and you can actually place your mirror as a thin film versus actually having an actual mirror on the end. And so we pump it at 780, and essentially 795 because of the atomic transitions of rubidium comes out the other end, and it gets reflected back. Another highlight of the research is the calculation of the electric mobility and the diffusion coefficients of rubidium through selected film under the high power conditions. So what we find is that the electric field actually, as it increases, the mobility of the rubidium ion actually decreases. And so that was another highlight. So really, this might have come first, but I just thought I'd get the other stuff out of the way. But reason, why are we doing this? There have been 30 years of research on Diode lasers, successful kilowatt class lasers, the chemical iodine oxygen laser in 2010, and earlier, semiconductor diode lasers. Boeing has been known to fire lasers for maybe 18 hours, 100 kilowatts in 2010. The disadvantages includes size, weight, heat dissipation, efficiency, and logistically, they're not very easy to use, okay? They're also very difficult to combine multiple lasers. So the combination of what we get in a DPAL is that you can flow a gas and you can remove heat really well. You can combine multiple pump laser beams with efficiency actually higher than 95%, and has a very small footprint. So this can actually be scaled to megawatt class, but we can't scale it to megawatt class until we have sufficient confidence of materials that can actually prevent this thing from just blowing up. Okay, so the application is military, and there's some medical applications as well. And clearly, most DPAL gain cells are easily destroyed by atomic alkali. So the use of a nanometer layer of thin film to protect the gain medium is actually a very inexpensive and readily available solution, but the right combination needs to be made. So this is a functional block diagram of the DPAL. What you have is a laser diode or a diode array pump. Oh, very color. So then you pump this into a gas or a vapor laser gain medium, and then you have an output beam. So you're coming in with 780 here, and you're leaving out with 795 nanometer. So basically a wavelength shift of about 50 nanometer. Now, just to show you the scale of this type of laser, I mean, look at the numbers here. Look how small. I mean, 2.5 centimeter, that's the alvin with the gain cell. Then 10 centimeter between the polarization beam splitter and the 12.5 centimeter. So the scale of this is really very, very small. And so you start with a diode, the quarter wave plate, get your polarization, then you focus the beam, you split the polarization here, S and P go in different direction, and then you go through the gain cell here, and of course it resonates. The reason why this is called a resonator section is because this process goes back and forth, back and forth. This is a highly reflective mirror until the laser finally just shoots out. And here's some references towards that if you want to read that. So taking a closer look at the laser, basically, I guess you've seen this before in kind of a summary, but what's different here is that we show where we will apply the thin film. So we apply an anti-reflective film in front of the 780 nanometer beam, usually a quarter wavelength of, could be magnesium, fluoride. In this case, because of the high power laser, you may want to use something different. So we have an inner thin film coating here, which should survive contact with the atomic rubidium. And so what you have is, typically we use fused silica, and we have a highly reflective mirror behind it. So really you have two pieces here, and eventually we'll end up with just one piece at the end. So this mirror, we turn it into a thin film. So, but you see, it's helium plus atomic rubidium at 200 degrees Celsius. So if you're unfamiliar with the quarter wavelength theory, basically, essentially what you have is, it uses a quarter wavelength dielectric stack using multiple layers of thin film, mag fluoride. You increase the laser, the AR coatings increase laser throughput at prescribed wavelengths, so you have much less reflection. Basically, the incident beam cancels out the reflected beam, and essentially you can have almost zero reflections on the surface. So as far as rubidium-induced glass failure mechanism, there's been a lot of work done in this area prior to this, especially by the Aerospace Corporation. I'm sure you're familiar with those folks. But as far as why do we choose rubidium? So, rubidium has atomic number 37, and basically it's a soft and silvery white metal if you've ever handled it. Easily vaporized, so slightly above room temperature. It has a convenient spectral absorption range. So for DPAL, we're only interested in wavelengths of 780 to 900 nanometer. So it's actually used a lot for laser manipulation of atoms using the glass envelopes of DPAL gain cells in rubidium discharge lamps as a critical component for satellites. Basically, you can use it to cool for laser cooling, and as well as the Bose-Einstein condensate, as well as in surf magnetometers. So the biggest concern for any of these applications is, how is the rubidium vapor going to react? And Aerospace Corporation studies have shown that it has actually reduced the lifetime, and these are things that can be calculated of the actual laser itself. And Volk is one of the more prolific authors on that. So, this part kind of deals with the reaction of a gas with a you can think of it as a reaction of a gas with a quiescent liquid based on the kinetic theory by Dan Wickertz. So glass is simply a liquid of very high viscosity, no saturation effects. Diffusion of the condensed plane is arbitrary. So there are different levels of diffusion that can occur, surface versus bulk. And this theory is actually useful for the analogy for reaction kinetics across a phase boundary. and it can predict the consumption of the rubidium as a function of temperature over time. I guess what we could take away from this is the two damage mechanisms for glass. One is chemical reaction, requires high activation energy, and one is rubidium diffusion in the glasses. And so there are equation and theories that predict the overall transfer of rubidium across the phase boundary. And so you can see it there. And basically, the major metallic rubidium loss mechanism is diffusion in the gain cell glass walls over time. So in general, a diffusion rate of 3 times 10 to the minus 14 centimeters squared per second for rubidium infused silica. And it turns out also one of the important results is that people expect that the diffusion will only be surface, but oftentimes, as far as 2 microns into the material, the rubidium is there, and they were trying to figure out how did it get there. So it's more than just surface, it actually goes deep into the material. And that's why it's a dominant loss mechanism. So, I mean, how can we consider what the process is, what goes on here? So the model for rubidium absorption in silica glass, so after it gets ionized, it's incorporated into the crystal, you have vacancies generated, and the rubidium vacancies capture available neutralizing and form F centers. Sometimes they form, F centers are generally, they're different from paramagnetic centers. They're color centers. Basically what you have is a wavelength shift. And B. Samuneves have done a lot of work in this area. And the whole idea is that the lattice, the atomic structure is basically modified, the lattice structure, whereby you now have a shift in the wavelength, which causes it to either absorb at a different wavelength, or just basically degrade performance at another wavelength. So basically, the rubidium atoms in the vapor penetrates or diffuses into the glass network. It breaks a bridge in SiO-Si bond, releases the electrons, orbits around the negative ion vacancy. Rubidium ion in the interstitial position, and people have different theories, but to really capture it,